Okay, so hi everyone, this is Sean Mullery from Electronic Engineering at IT Sligo, and in tonight's lecture on machine learning we're going to be looking at support vector machines, which are a very important model type or training type that we use for machine learning. So once again, these are used for classification, so you can kind of think of them as not necessarily as a competitor to logistic regression, but certainly another option beyond logistic regression as something to use. So what we're going to do is we're just going to have a look at an example here of some data and have a think about what are some of the problems associated with it, or how might you go about separating this data. So one of the issues that that's faced by some of the other types of classification is that if you can separate the data quite well, you may not separate it in absolutely the best way. And remember that this is our training data, so we can't guarantee where the other other data samples within that same process might appear from. So once we learn our model, if we get a data sample that's that's maybe not covered by what our training distribution showed us, it could easily fall outside what the model is doing. So the idea of the support vector machine is to try and find the best line for separating this data, and it does that by having a think about what is the widest margin that we can find if we're going in a straight line through this data. So I want you to imagine that you've got a ship or something like that. So I want you to imagine a very long ship. So a rectangular ship here, and the ship is trying to sail through this gap here. Okay. Now you can see there that at the moment that this ship is a bit too wide to sail through the gap, but we could have a smaller ship like that. And what we wanted to do is we wanted to come through and we wanted to sail through the gap in between these and not touch any of them. So what is its best route to take if it can only take a straight line? If it has to go in a straight line, what is the best route for it to take? And therefore, what's the widest ship that we could get through these without actually hitting the data on either side? And that's the idea of what the support vector machine does, because here's the problem. We can easily make a kind of a linear model to separate this data that does something like this. Okay, now you can see that separated the data quite well, but we can take another example that might do something like this. Okay, and we'll make it even more so. We'll bring it right up to the line there. Okay, and we'll take maybe a third one, and we'll go straight down through here if it'll let me. Okay, you can see that one there is coming closer. I think that's not a perfectly straight line, but it'll do. So there are all these different possibilities. We can of course come up with other ones as well. We'll maybe go for a red one here, and we'll just go straight down through the center there, like that. Okay, it's not doing a straight line for me. There we are. So the question is, which of these lines is the best? And I think, if you look at the data, you can see that the red one might be the better one to choose rather than some of the other ones, because it keeps the maximum distance that it can away from the data on either side. And that's really what the support vector machine tries to do. It tries to see what is the best line that separates this data that keeps the maximum distance away from the samples that are closest to that border. And by doing that, it makes the best separator. Okay. Now, of course, what we talk about as a straight line here in higher dimensions becomes a plane, and in higher dimensions than that again becomes what we call a hyperplane. So normally you'll hear this described as being a hyperplane that separates the data rather than just being a line. But because we're going to look at this as in two-dimensional examples, we'll think of it in terms of a line. So what I'm going to do is I'm going to delete the ones I don't want here. Oh, we've deleted them all, so I may as well go back and start again. So imagine I take a straight line here. Straight line. Okay. And I try and get that so that it's kind of got the maximum distance going on either side. And what we can then do is we can kind of think about what the margin is on either side. So we've got it hitting there on that side, and we've got it hitting these ones on that side. Okay, so you see how, maybe we'll just put those as a different color here just so that you can see them differently. So we'll put them as purple. So those will be the margins on either side, okay, of this line. And what happens is the support vector machine system, or the training system, it tries to find the correct orientation of that red line so that it can maximize the margin, this gap here between these, and those gaps should be identical to each other. It wants to maximize those margins there so that it can have the widest kind of boulevard that goes down through the middle of this, that separates the data and keeps that red line being the best separator. Once it does that, it then has the best red line there for separating the data later. So once we end up on either one side of that line or the other, that's our classification done. Okay. So the idea of the support vector machine is to find the best linear separation between classes. It tries to find the separation that gives the largest margin between the different classes. Unlike logistic regression, it does not give you a confidence value. So once we've our training done, it says it's on that side or it's on the other side. So it's positive class or negative side, or negative class. It doesn't say it's 70% this and 30% that. Okay. However, SVM has computational advantages over logistic regression, and it's also easier to optimize. So it means that it can optimize faster, and it can optimize a little bit easier in many cases. And so for that reason, it can be a very powerful technique to use over logistic regression, even though it won't give you a value of its confidence. Now, as it only requires some of the data points, it can work quite well with small data sets. So this is something that we're going to come back to in a minute, but you can see here that when it's making its decision, it clearly doesn't need to include this one over here, for example, or this one over here, or maybe some of these ones here. You can see it doesn't need to include those because they're nowhere near the border. So in actual fact, the ones it needs to worry about are that one there, that one there, and that one there that's under it, and beyond that it doesn't need to worry too much about what it's dealing with. So for that reason, you can actually get away with having quite small data sets. Admittedly, you still have all the problems with having a small data set in that it mightn't very well represent the overall distribution of the data underlying it, but nonetheless you can still get away with some fairly small data sets and still come up with a fairly good model. So it's good from that point of view. It's also good at dealing with high dimensional data. So sometimes what happens when we've high dimensional data is that we don't really have enough samples to represent all that high dimensional data, but we find that SVM can work quite well in those circumstances as well. Okay. So it's a constrained optimization problem, and what we mean by that is SVM must optimize the margin while still meeting the constraint that it correctly classifies the data. So it can't just decide, if we go back to our example here, it can't just decide to have those purple lines go wider and wider and wider if, for example, it ends up with that red line not being good. So for that reason, it has to both keep the data separate while also trying to make that margin as big as possible. So that's why we call it a constrained optimization problem, because it's got constraints on the optimization that it's trying to do. Now, constraint optimization problems usually require a thing called Lagrange multipliers to solve them. Some of you may have covered those in maths. I don't know whether we do it here in IT Sligo, but has anybody come across these Lagrange multipliers before? Okay, so Stephen has heard of them. Anyone else? No. Okay, so don't. Yeah, so Maria has heard and Jerry no, and yeah, Olivia did probably heard of them at some point in the past. Don't worry too much about them. They're nowhere near as complex of a problem as you think, but we're actually going to somewhat gloss over them here tonight. We're going to mention them. We're not going to go into the detail of them because it's not really vitally important what we want to do. But just so that you don't feel that they're being completely left out, if you look at this Patrick Jones maths tutorial, Patrick JMT on YouTube, he does a really nice, very, very small and simple example, if you click on that link, to just explain the general idea of what a Lagrange multiplier is, so that you can kind of get the idea. And it's basically that it may have been, I think that could be the Lagrange point, Jerry. I wonder, is that's a slightly different thing, which is a point between two bodies. I unless I haven't seen that film, so you could be correct. But in any case, basically what happens is that they kind of have a change of variables. They add in an extra variable in order to deal with the with this extra constraint that you're trying to add into the problem. So they're a way of dealing with that. But you can have a look at that little example just to get an idea of it. So now what we're going to have to do is we're going to have to talk a little bit about straight lines and how to model them. We've done a bit of this already, but we're going to look at this in a slightly different way now, particularly when it comes to we've two input dimensions and how we're going to deal with a straight line in that particular case. So the equation of a straight line can be given as y equals ax plus b, or we had mx plus c. There's a few different ways of writing it. We're going to use w as our parameters, or our weights. So we would write this as y equals w0 times x plus w1. And that's if we've only one input variable x. But we're going to find that we've got a whole vector of x which can deal with multiple dimensions. So we need to extend this from a straight line to a hyperplane, and for convenience we will separate the bias weight out. So instead of having a w1, we'll call that b for the moment, make things a bit easier on us. So we'll separate that out from the rest of the weights and we'll call it b. So what we would now have in order to determine y is we'd have w transpose x plus b, and w and x can be any number of dimensions as long as they're the same number of dimensions. So if x happens to be in 5 dimensions, w would have to be in 5 dimensions as well, and then we'd have the 6th dimension being b, or the sixth weight being b, which would be the bias. Okay, so let's talk a little bit about lines here. And so what I'm going to do here, just in order to remind you, and I'm sure those of you that did linear algebra last year will have come across some of these concepts. Those of you who are doing it this year, it might be fresher in your mind. So what I'm going to do is I'm going to draw, I'm going to assume that we're in 2 dimensions here. I'm going to draw my vector w, which I've done there, and I'm going to talk about what are the sort of things that happen in order to for us to define a line. So if my parameters is w there, and I'm going to pick a we'll pick an x here, maybe go for a smaller x there, and I'm going to pick a dot here. And basically what I'm saying is that this is another vector here. And so we'll draw a line to that. Didn't draw that very well. Okay. Now, can anybody tell me what I'm doing when I do something like I've written there, which is w transpose x? Does anyone know what I'm doing there in terms of linear algebra and in terms of geometry? No, nobody's biting. Okay, so what I'm doing here is I'm projecting x onto w here. Okay, just making sure you're all still there. So I'm projecting x onto w, which hopefully you've come across that idea. This is basically a cross product in linear algebra, right? So I'm projecting x onto w, right? So what does that look like? Now the thing is that I've deliberately drawn w as being quite short here, so that you kind of you know, if I was to draw it long, it might be quite obvious how it projects on. But if it's small like this, it's not always obvious. So basically what will happen in this particular case is I can continue to draw w out in this direction. Just move it there slightly. I'll actually just draw it again. Okay. And what we do is we project our thing onto it. Okay, so at 90 degrees to it here. Are you familiar with this concept? Have you seen this before? Yeah, okay, so you have seen this sort of thing before. So you can see here that that w doesn't actually have to be that long. It's just going in the right direction, and once we project onto it, we're going to get something like that. Okay. So when we say w transpose x, w transpose x plus b equals 0, you can see here that we're not ending up at a 0 position, we're ending up somewhere else. So we can actually think of this as W transpose X equals minus B. Okay, and in effect what we're saying is that this distance then from there to there is minus B. Now you might think, well, that's going in a positive direction, but that happens to be just the one that I've drawn here. In other words, that's going to be the length that we're going to have there. Now, because B is a single number, it's not a vector or anything like that. It's a single length. Now the thing is that it's very easy to get confused by whether it should be minus B or plus B and things like that. So what I'm going to remind you is this. I could have written this as W transpose X minus B equals 0, and it would have worked just as well. And the reason for that is whatever B happens to be, inside of it, B, we could have, like, let's say minus 5 or something like that. And therefore the minus and the minus are going to cancel each other out. So as long as you're consistent, you don't need to be too concerned about whether that's a minus B or a plus B and what direction it's going in. Okay, or whether it's minus or plus. Okay, so are you familiar with this idea about that distance out there, about that being a or do you know what W would be called here if we called this if we drew a line, let's say from there down in that direction there, draw it again. So let's say that's my line there, that red line. What's W called with referring to that line? What I mean there is that we've got a right angle here. Does anyone know what the name? It's not the slope, actually. No. It is indeed, yeah. Okay, it's called the normal. Okay, so it's normal, and by normal we basically mean perpendicular to it. Okay, so this is an interesting thing because oftentimes we think when we're learning a model and W is the model that we're going to learn, you think that that's the line itself, but it's actually the normal to the line is what we're learning, and we then figure it out because it's a single vector. Okay. Now, when we come to trying to figure out what we had back here, which was we really want to figure out where that red line is there, but it might help to figure out where the purple lines are. Okay. So what we're going to do is we're going to use two vectors. So what I'm going to do is I'm going to assume that I've got a vector here called vector x1, and that's what I've done there. And then I'm going to make another vector. I'm going to call it x2, and I'm going to assume it's let's say it's over here somewhere. Okay, so it's there. And what we'll do is we'll draw a line to it. Do that again. Okay. And once again, we can do the following. So previously we had what we actually had was we had W transpose x1 plus B equals, and I'll come to in a moment what it is. You can see it's there. We're actually going to set it at 1 rather than 0 for a reason. But what I'm going to do in this particular one is I'm going to do W transpose x2 plus B equals something. Now clearly those two can't equal each other because they're not in the same places. They're not performing the same line. But both lines are perpendicular to our W vector. Because we're projecting onto that W vector. So both the lines that we're going to create by this are perpendicular to that vector, which means that they're parallel to each other. Okay, so once again, I'll just draw the projection there. It comes to that point there. Okay, and we've called this x2. Okay, so let's imagine that I've got lots of data, and two of the pieces of data are x1 and x2. Okay, you can see here that they are actually vectors. Okay, and we refer to them as the support vectors. Okay, the support vectors, and that's what the name of tonight's lecture comes from. It's the support vector machines. It's the machine that uses support vectors in order to determine its thing. Now, let's imagine that x1 is of the negative class and x2 is of the positive class. What we're saying is we want those to be either side of the line. So where should we draw the line that separates the different data? And the answer to that is that we should draw it perpendicular to that and perpendicular to that, guys. So if we just draw it there, perpendicular to those dotted lines there. Sorry, not perpendicular, parallel to those dotted lines, and exactly halfway in between. Okay, so somewhere down the middle, down like that. Okay, is that halfway? It's probably not far off. I'll maybe just move it slightly to about there. Okay, so that's going to be our dividing line. And what we would normally say then is we would we'd get rid of this guy here for a second. Right, delete that. And this would be my important point here, which would be b distance along the w vector. So we'll draw like that. That's b distance along that. What are these guys? Well, they're going to be some distance, and they need to be exactly the same distance away from that center. So they're basically going to be, this one might be b minus 1, and this one might be b plus 1. Okay. Is everyone with me so far? Are you following what I'm saying there? Is there any questions on what I'm saying? All good. Okay, so nobody's yeah. Okay, so because nobody's saying there's anything wrong, I'm going to continue. Now, this comes then to what we want to do is we want to find these ones with the that we said W transpose X plus B equals 1, or W transpose X plus B equals minus 1. They're going to be our margin lines, okay? And we're going to decide on those based on some of our samples, which are the ones that are going to be right on the margin lines, okay? And they're called our support vectors. And they're called support vectors because if you think about them, they kind of jam their way in there in the gap. And they're what causes us to have exactly the perfect margin that still goes through. Okay, so we're going to call them x1 and x2, and we're going to pick those as points. The important thing is that we have the labels. So let's say, for example, we'll have a positive label and a negative label. Now, once again, it doesn't matter which are the positive labels and which are the negative labels. It's just the same as the B. It doesn't matter as long as we're consistent. So what we're saying is that this is going to come to be minus 1, which of course if we just take the b over the other side, that'll end up with minus b minus 1, which would be the same as b plus 1. Or we have the plus 1 here must equal that plus 1. As long as that's the case, then you'll keep yourself right, and everything else will turn out correct. So you don't need to get too worried about what's minus and what's plus, as long as you keep them consistent. Okay. The second thing is that we have a tendency to think of this margin here, in other words, that gap there, as being the value 1. Okay, but that's not strictly speaking the case. And so we'll maybe, what I'm going to do is I'm just going to copy this onto my next slide here, which is where we talk about the gap. So that gap is not 1 in the same way as the following. So what I'm going to do is I'm just going to kind of use an old mathematical technique here. I think you'd all agree with me that A is equal to A. Okay, I think that's a true statement. But if we say 1 multiplied by A is equal to what? What would you say there? 1 multiplied by A, and there's an obvious question, so there's no trick here. 1 multiplied by A equals what? Nobody typing? Can you hear me? Okay, there's a few A's coming in there. Right, so 1 multiplied by A equals A. That's fine. Okay. Now what this is basically saying is that 1 is called the identity. It's called the identity for multiplication. And really, what's important here is the A rather than the 1. Even though 1 is important by saying that it's the identity, it's the A that's important. Now, very much in the same way, that 1 and that 1 there, they are just used as the identity here. So it's something else that's actually going to define what the gap is. It's not the 1 itself. It's just that we're going to multiply 1 by that gap, whatever it is. Okay, so that's important to get into your heads, because I know certainly when I first looked at these, I thought there was something special, that this distance had to be 1, but then I didn't understand the idea where we were saying, well, we're maximizing the gap, or we're maximizing the margin. Well, is the margin just what is it not just 1, but it's actually we're maximizing the number that we're going to multiply by 1. Okay, so what we can do is we can basically subtract these two values from each other, x1 away from x2. And that's what we have up here. So W transpose x1 plus b minus W transpose x2 plus b equals to 1 minus minus 1, which of course comes to 2. Now, effectively what we're doing here is we're taking, and we worked through the maths here. You can see that what we're doing is we're just manipulating this out. We're multiplying that out. The plus b minus b, they're going to cancel each other out. What have I done? There we are. Sorry guys, I'll just maximize that on the screen again there. Okay, so minus b plus or plus b minus b, that'll just cancel each other out, and we're left with this W transpose x1 minus W transpose x2 equals 2. We can take out the common W transpose, and we have x1 minus x2. Now x1 minus x2 are our two support vectors, and what that basically means in this case is it's basically a line. We'll take maybe a different color here of orange and draw a line between these two. Okay, so you can see that line there, but importantly what we're also saying is that we are going to project that onto the W vector, and if you project that, you're basically going to go along those lines there and along those lines there, so it's going to end up being the same anyway as we had already drawn. Okay, now the thing about that is that we want to find out what the length of B is there effectively, because what we have is we've projected it onto W, but we don't exactly know what the length of W is. So what we can do is we can try and make sure that W is a unit length vector by dividing by the length that W currently is. So if W is small, we divide by a small number, and that will bring it up to 1. And if W happens to be bigger than 1, we divide by that number, and that brings it back down to 1. So we put in this element here, which is the norm of W, or the length of W, and we divide that into the W vector, multiply by that, and we do that on both sides here. And what that will now tell us is what the actual gap is between these two. Okay, now the 2 is simply because we've got the gap on either side, so you can think of this as that gap is 1 over the length of W of the W vector. Okay, now what does that mean in terms of what we want to do if it's the length of W? Well, what it means is that, remember that we're learning those W weights, so if we learn those W weights to be smaller, what happens my gap? Okay, so if I learn the W to be smaller, what happens to the overall gap? Yeah, it becomes larger. So we want a situation where that becomes as large as it can get and still classify the data. So therefore we're going to try and learn for W to be smaller. Now remember that learning W to be smaller does not affect where that line is put at all. Okay, just because W is smaller just means that this arrow down here is smaller. It can be very, very small and still pointed in the right direction, and if we project onto it, it's still, the line is going to be in the right place. So don't worry about the fact that setting W to smaller is going to put that line in a different place or anything. It's not. Certainly the W has to be in the right direction in order to make sure that the line is correctly oriented, but its size can be any arbitrary size, but clearly the smaller it goes, the larger our gap is going to become because of the maths that we've worked out here. Okay, so so that's what determines our margin lines, and we're going to have to try and maximize that gap. So the gap is equal to 2 over the size of W. Okay, not anything to do with its orientation, just its length. So what would we have to do to maximize the gap? Well, we'd have to try and make it smaller. How do we make it as small as possible? Well, we could set it to 0. this would make the gap infinity. Okay, so if you think back to our example back here, this would make this gap that it could go all the way out here and go off the sheet. The problem with that is that if it goes all the way out and off the sheet, it's no longer guaranteed to classify the data correctly. So that would be a problem. So remember that this is not just an optimization problem of let's make W 0. It's let's make W as small as possible, but still separate the data. It's a constrained problem. So so it wouldn't separate the data. So remember, the constraint is maximize the margin while still meeting the constraint that it correctly classifies the data. So we'll want to make W as small as possible while still classifying the data correctly. And that's why we're going to have to include more than this in it. Now, what we're going to do here is we're going to do a little bit of what we call mathematical convenience. So this is where mathematicians see a problem coming down the line and change their problem to suit what it is that's going to happen to them. Okay, so it's true to say that if we want to, remember, we want to minimize W in order to maximize the gap. Or minimize the length of W, I should say, rather than minimizing W itself. So minimize the length of W in order to maximize the gap. But it's true to say that minimizing W is the same as minimizing W squared. Okay? In other words, the minimum point of W is going to be the same as the minimum point of W squared. So therefore, if we can minimize W squared, we minimize W as well. Why would we minimize W squared instead? Well, it makes it into a quadratic problem, which is easier to find the minimum of. Okay, so it's what's called a quadratic programming problem, and it's easier to solve. So therefore, we'd automatically go to make it a squared problem rather than the other one, because it'll give us the same result and it'll be easier to solve. So if you have two equivalent problems, always solve the easier one. And while we're at it, it's true to say that minimizing the length of W squared is the same as minimizing the length of W squared divided by 2. We'll normally solve min-max problems. Well, actually, how do we find the minimum of a function? Can you remember? I was trying to remind you of these things. How do we find the minimum of a function? Yep. So I think between all of you, you've come up with the right answer there. So you get the derivative and then you set that to 0 and then you solve for wherever that is. Okay. So why might we decide to make the function divided by 2 instead of not? And you can see there that what's going to happen is when we get the derivative with respect to W, that squared term is going to come down and move to the front. And therefore, it's going to get cancelled out with this 2 here. If we don't have it, then we're going to have an extra 2 on the edge, which is a little bit more difficult to deal with. It's just a little bit more complex. So why not just make this problem divided by 2 in the first place, so that when we get the derivative, that problem is going to be gone. And that's why they do. So it's important that you understand that this is all under the guise of mathematical convenience. It's not that there's anything special about what we're doing here. It's just to make life a little bit easier on us down the road. Okay. So that's why they do both of those things. So remember, we're minimizing the length of W so that we can maximize the gap. So we've decided instead that we're going to minimize the length of W squared divided by 2. And that's also going to maximize the gap. So we mentioned these Lagrange multipliers, and as I say, I'm not going to work through the maths of these or explain them. But basically, these are a way of doing that minimization while including the constraint of making sure that you actually classify the data, so you don't just minimize W. So the result of using the Lagrange multipliers comes out as this. And if you want to see the workings of that maths, and I'd invite you to do so, Patrick Winston from MIT has a YouTube lecture in which he goes through it. So it maybe takes it's about a 40 or 50 minute lecture, but the section that does that is maybe only 10 or 15 minutes long. So he comes up with this this solution here, which is that he's maximizing this with respect to a new variable called alpha. And there's a few, this is subject to a few constraints, such as alpha I must be bigger than or equal to 0. So you have a pathological case if you just set them all to 0. And alpha I by yi equals 0, the sum of them all together. Okay. But what we're going to do is, rather than go through the maths of that, what we're going to do is we're going to just take a quick analysis of this function, so that we understand, what is the point of it? What is it trying to do? So the alpha values, basically what they are, this new variable that we've added, they are a weighting of how important a sample is. Now, we saw in one of the first slides that it's samples that are close to the dividing line, they're the important ones. The samples further away are of no particular use to our function. So therefore, the ones that are further away would have samples that have this. So alpha I by alpha j, where I and j are two different samples, are equal to 0. And what that basically means is, it doesn't mean that alpha j is equal to 0 or that alpha I is equal to 0. It just means that one of them is, and therefore in that particular case, the interaction between the two of them, we would basically say, well, there's no interaction here. So what that basically means is that if you've got two of these that are far away from each other, they don't really have an interaction there, and therefore the multiplication of them would get multiplied by 0, and we wouldn't really include it in our maximization here. That's the first thing. Second thing is our two labels that we would label them. And remember, we label positive classes as +1 and negative classes as -1. So it's not 0 and 1 in this case. It's +1 and -1 because of that either side of the barrier that we're going, and we want to be 1 either side of it. So yi by yj, in other words, two different labels. If the labels are different, in other words, if they're a positive class and a negative class, this will add to the overall maximum. Okay, so in other words, we'll get a bigger maximum if we're dealing with two samples that are different from each other, because that's important, where we're trying to get the separation happening there. If, on the other hand, the two samples are the same as each other, well, that doesn't really help us in maximizing the problem, and therefore we'll pretty much ignore those. Okay. The third thing is, and I've a mistake in the original set of notes, so if you have the notes there in front of you, you need to put the little transpose in there for that. What we're doing is we're projecting each vector onto another vector. And if we project, if two of the samples are close together, when we do that projection, we'll get our largest value. Whereas if they're far apart, the amount of one that projects onto the other will be smaller. So in this particular case, if they're very alike, this will give the largest of values, and hence this is concerned with samples that are close together. So basically, overall, what's going to maximize this? Samples that are close to the boundary, close to each other, but opposite in label, they're the ones that prove to be important. And that's why we say with this problem that it really only takes account of the ones that are close to the boundary. They're the ones that are important for actually separating the data, and the rest don't matter. Okay, those are the ones that they take into account. And this function, this function takes that into account, but this is not necessarily what we'll do. Instead, we prefer to minimize things, and we'll probably have a different way of accounting for this, and we'll show that in 1 or 2 slides time. First, I want to talk about this parameter, which is called the C parameter, and it's a way of trading off these two things. So we want to maximize the margin while still classifying the data. And the question then is, how do we trade off those two things? Obviously, if we can do both of them perfectly, that's great. But which is better? Is it more important to maximize the margin, or more important to classify the data, and to what extent? And this is what the C parameter trades off. Now, you may remember we did a little bit on regularization when we were talking about logistic regression, where we wanted to classify the data, but we also wanted to keep our parameters small in value, and that was had a 1 over lambda. This is very similar, except that the C is equivalent to the 1 over lambda. It's just it's put into the other side of the function. So let's have a look at the example that I've shown here, which is that there is no straight line that I can make. This looks close to a linearly separable thing, but as you can see, if I was to draw a straight line here, probably the best I could draw is something down the center there. But we've clearly got something wrong on one side and wrong on the other side as well. Okay, so it's not linearly separable. So how do we deal with this in this situation? Can we still have a straight line, and what happens? Because clearly there's no margin that we can use here that's actually going to still keep us within it. So what we've got to do is we've got to trade off the fact that we're not going to classify this perfectly with with how wide of a margin we'd still like to design in order to have this line that it's still correctly oriented to give the best separation that we can get. Okay, and it's that trading off that this C parameter does. So here's the C parameter there. It's put on that side there for us. And this is the overall loss function. And I think it's worth spending a few minutes on this loss function in order to get an understanding of what we're dealing with. So remember, what this loss function, particularly this section here, well, actually the whole lot of it is to try and mimic this thing here. Okay, so we're going to try and do the same thing. And what we're basically going to say is that we want samples that are close to the line to be the important ones. We pretty much want to ignore samples that are well beyond the margin. They don't matter. So how are we going to do that? So we use a max function here, and what we basically do is we look at this section here. Okay, now the one here is that one that I said that was the identity function. Okay, so it in itself does not define the maximum, the size of the margin. It's actually it in relation to the W transpose on the B that causes that. So let's imagine that we have one of the positive classes. What we're going to have in this case is that what's inside the brackets here is going to be a positive number, or should be a positive number. So we expect that to be a plus. Our label is going to be a +1, so that will also be a plus. But we're multiplied by this minus here. So we've got minus by plus by plus. So what do you reckon that will, the three of those together, will they come up as a minus or a plus overall? Yeah, so that'll come up as a minus. Now, what about the other situation where we're dealing with a negative sample? So in the negative sample, this is going to be a -1. These are going to be minus numbers in some way, or they want to be heading towards minus numbers if they're good. And we've obviously got a minus there. So we've got minus by minus by minus. What's that going to give me? Yep, so you've all gone for minus there again. So what we're basically saying is that no matter, because of the fact that we're multiplying by the label, if our samples here are, shall we say, heading in the right direction, okay, becoming a number that's going in the right direction away from the barrier, then that's good. And in that particular case, if they are, if this and this combined become more than 1, then overall this becomes less than 0. So it becomes less than 0. Okay. So maybe just delete that and just say that overall, no matter which direction we're going, if this section becomes bigger than 1 in going in the right direction, then overall this becomes less than 0. And what that means is that the maximum of the function, if this happens to be less than 0 and this is 0, we will have 0 come out. And that happens if we go over that margin line in either direction. So the only things that are going to get added in here are ones that when we tot up what's in the brackets here, if this comes to less than 1, okay, overall, when we put all of this together, if that comes to less than 1, then these two combined will come to slightly more than, bigger than 0. And so whatever number they are, let's say 0.3, 0.4, whatever they are, and they will get added in to, our loss. Okay, so they're the only ones that are going to contribute to the loss. And what that does in effect is it makes sure that any samples that are a long way away or outside those margins, they don't contribute at all. The ones that contribute are the ones that are inside the margin. Now, what that basically means for our function here is that if we ignore this part over here for the moment, and we just think about this one here, what's going to happen is it's going to try and learn W, and it's going to try and learn a B that is going to be done in such a way as to make sure that as many of those samples are outside of those margins. Okay. And if they're outside those margins, they don't count. However, it is important to understand that as those margins begin to tighten and tighten and tighten, at some point they'll hit the last of our samples, and they'll be correctly oriented to hit the last of our samples. If they move even slightly beyond that point, it makes no difference to this section here, okay? Because they no longer have an effect. They're no longer adding anything more into that maximum. So once we get the last few of those outside of the margins, this no longer has an effect. However, this does. And what this does is it tries to push the margins out further. So every time we bring it, that we're bringing it in, this other one is trying to push it out further. And they should meet in the middle at the point that they hit those support vectors. Okay, so those the few vectors that are important, they will be the ones at which we land in the middle. However, if we want to trade off and say, actually, it's not vitally important that we can have a few of those vectors inside the margins, then what you can do is you can say that this C is not as important. Drop it in value and say that maximizing the margin is more important by this being less important. Okay, so that's a multiplier by that. On the other hand, if you absolutely want to separate the data as being important, then you can put up the value of C, and that's more important than maximizing the margin. So this is a decision that you would make, and that's how you would do it. Okay, so what would be the word for C? You've seen it loads of times now at this stage. What would we call C? It's a particular type of parameter that we decide. No, because we're not going to learn it. It's we decide it. It's not, it does begin with H, but it's not heuristic. Yeah, hyperparameter is the term that I'm looking for, because we've used it. So what we're basically saying is that our value of C, that's a hyperparameter. So that's something that we're either going to tune or we're going to try and just decide it ourselves. It may well be based on a heuristic or otherwise, but it's not something we're going to learn. Okay. So what we need to do is we need to minimize all of this with respect to W. So just bear in mind once again that if we make W smaller, that makes the margins wider, okay? And if we basically change it in this way, that's going to make the margin, or if we try and minimize this part, it's going to try and make the margins a little bit tighter so that it can fit the two. So here's a few examples of data, and you can see hopefully there. You can see the positive and the negative classes there. Now what I've happened to do, I ran through some examples of this, and I basically changed it until I got C at a value of 140 in this particular case. You mightn't expect it to be that big, but that very much depends on, we're summing up the number of weights, and if we only have a small number of weights, then that doesn't come to a big value. Okay, so this is why it's important to kind of try and get the right value for C. Now if I brought C above 140, it brought no improvement in terms of classification. So that was our limit here, where we have our support vectors. It's those three. Our margin can become no wider in this particular case once we have a value of C equal to 140. And that basically means that this is so powerful that we're not allowed to maximize any further without making matters worse. But if I drop the value of C, that's going to allow me maximize a little bit further, and before we have an equalization of these two. So that's what I've done there. I've made C a value of 100, which is a smaller value, and we can see the effect of going below 140 in this case. What's happened is these two have maintained their position, but the line has moved over to there, and that vector has now moved inside of the margins. So we're getting some loss from this because it's inside the margins. So that's going to create some loss here, but it's going to be equalized by the fact that our margin has now been wider, and that's obviously what we want in this particular case by choosing that. What happens if I go even further? So we have our C equal to 100. If I go even further than to 50, well, what's happened is I've now included yet another support vector in this, and this one here has actually moved over the margin line. So even in our training data, that's going to be getting it wrong. It's going to be misclassified in this particular case. But that may suit us because we've now got a wider margin and we might want that for what we're doing. So it really depends on what it is we're looking for when we go to do this. So what happens if the data just isn't linearly separable? And I showed you an example of that where we had data that just, it wasn't linearly separable. What do we do in that particular case? And so you can see here that what we've done is I've set C to a very, very large number here. Makes no odds because we're still going to have some of these getting them wrong no matter where we put the line. We've included a good few support vectors in this now at this case. Even though we've ignored all of these ones here, we've still got all of these ones. And you can see the way that it's kind of divvied up the thing. It's come up with a reasonably good separation, but it's never going to separate it perfectly. If I set C to even smaller, then it's going to let the margin go even wider while still accepting the fact that obviously it's not classifying the data. So therefore classifying the data becomes less important when we set C to a smaller value. So C still has an effect in this case where it's not linearly separable. Okay. But let's go a little bit beyond the example of that we just showed there and say what happens in something like this case here where the yellow and the blue are the let's say the negative and the positive samples. We clearly can't separate this with a straight line. If I was to take a guess, I'd be going somewhere along there maybe, okay, to try and separate them so that, okay, I've got a few blues on this side and I have a few yellows on this side. I haven't separated it perfectly by any stretch of the imagination, but I've drawn a straight line and I've done a reasonably good job. Okay, so now it's clear that this cannot be separated by a straight line, but let's try just to see how wrong it goes. So we've done it there. I've set C to 100 because basically just kind of keep it at some value that was the same. And our training accuracy is 0.85, which that's basically saying that I've got 85% of them correct by doing this and only 15% of them incorrect in our training examples. Okay, so that's and I wasn't too far out with that line I drew there, I think, with what I came up with. Very close there. Okay, so that's the best line we can do if we're doing something with a straight line. But really, there are other ways of getting around this problem, and one of them is called kernel functions. So what I've drawn here is an example of where we might use a kernel function. So I want you to take a look at what I have here, which is I've got, let's say the blue X's are, let's say, the positive class, and I've got the purple circles as being the negative class. And I want to draw some hyperplane or line that separates these out. So you can see here that if I do the following, if I take that line, well, yes, I've got the blue on one side and these purples on the other side, but unfortunately these purples are on the wrong side of the barrier. What if I move my barrier to over there? Well, that doesn't really help the situation because now I've got, depending on which side we've done this, we might have the these being wrong and these being right, but unfortunately all the blues are wrong now as well. And if we take somewhere in the middle, which might seem the most sensible thing to do, well, unfortunately that still doesn't work because, of course, half of my blues and half of my purples are wrong and half of them are right. So that's not going to work here. So the trick, and it's often called a kernel trick, is to project it up into higher dimensions. So hopefully you can see there on a sheet in front, I've basically drawn this out on an actual sheet of paper. And we've got the same problem here. But to solve this problem, what I can do is I can project this two-dimensional plane into 3 dimensions. Okay, so by doing that, I can separate it now. So you can see here that there's a straight line across there and a straight line across here. You might be able to see the writing on it. But basically what I can now do is I can come along and slice through a plane there in this 3 dimensions, and I can cut the two apart. So the way of doing this is to project it up into higher dimensions. And by doing that, then allow us to, and we have to project it in just the right way, that would then allow us to have some other, either straight line or a plane that could then cut these apart in a straight way. So you're still looking for straight lines and hyperplanes, but what you're doing is you're adding in, or you're projecting in, some non-linearity up into a higher dimensions. It doesn't have to be 3 dimensions. This happened to be going from 2 up into 3. But we could have other situations where we're going from 5 up into 6. Okay, so all we're doing is we're projecting up into a higher dimension in order to be able to then have a separator that goes on there. But we've got to find the right function to multiply it by that, or otherwise, because if we did it, if you consider this where we were that way and I was to do it this way, then clearly if I slide along here, I'm not going to be able to separate them. So instead we perform what's called a nonlinear function or a kernel function on the data to project it into a higher dimension, 3 dimensions in this case, and then we see if a hyperplane can separate out that data. The choice of kernel function is problem specific, and it's often can be good to try several, and that's what I'm going to show you in this particular case. I'm going to try several of the common ones, and then we see which one of them works best. So one of them is called a polynomial kernel. So what I'm going to do is I've kept my value of C, because you really only want to change one hyperparameter at a time, and choosing a kernel is another hyperparameter. So do we choose polynomial or do we choose a radial basis function? And there are others as well. You know, that's again a hyperparameter. So we keep the other hyperparameters steady while we make this change. But of course, you could try other values of C and then try it through each of the different kernels to see which one would work best. So we're going to use a polynomial of degree 3. Once again, the degree of the polynomial is another hyperparameter, so do be aware of that. And this gives the following. So this looks like it's done reasonably well in terms of it, but actually what we find is that we've ended up with the exact same training accuracy as we had earlier. So it didn't really improve the situation. By the way, bear in mind, in case you're wondering how we got the particular shape we got, polynomial of degree 3 allows us to do curves that will turn, right? But what happens is that this will project back down into it, into doing something along the lines of this. So when we see it back on the 2 dimensions, we see something like this instead of seeing the actual curve. Okay, so it's projected back into 2 dimensions. So whatever we do in 3 dimensions, whatever the effect that we bring into 3 dimensions, we're once again just looking down on the problem. So as you say, you can try this with the polynomial, but actually, as it happens, it doesn't improve the situation over the straight line. If we use a radial basis function, and a radial basis function, there are many of them. You can think of these as like Gaussians or all sorts of different ones. But in effect, all we're saying is that there's some, you know, if we put in a value x, that's the same as if the x is in any direction, or so in any length. So if it's minus x or x in, you know, along any direction, basically will give us the same value. So that's what makes it circular or radial. So x is basically a radius in any direction. We get the same value for the function. If we use that on this particular problem, you can see that when it's projected back down into the 2 dimensions, it comes out looking quite like what the separation of the data would be. Just remember that you could picture this. You could see the kind of spiral nature of this. You could see that if we could really get in like that and do something like that, that was going to do a reasonable job of separating the data. And we can see here that the radial basis function has actually done a good job of coming up with that. It still doesn't do it perfectly, but it's done a reasonable job, and our training accuracy has now gone up to 0.96 or 96%. So in general, you know, when you get up to like 96%, getting to 97 and 98 becomes much harder with any of these models. So getting up to that value is doing pretty well. Getting from 85 up to 96 is pretty good. But getting from 96 to 99 would be even harder than that previous one. So in general, improvements become much more difficult the closer you get to 1.0. So keep in mind, this is training accuracy and not test accuracy. So once we come to testing, and this may be important just to kind of finish on this, really all that happens is this margin is forgotten about when it comes to testing. It's if we come up with a new value and it's there, then it's on the, let's say, the positive side of the barrier. Therefore, all we know is that it's given a positive label, and if it happens to be on this side of the barrier, it's given a negative label. So it's really about finding, the whole idea of the margins is to find this perfect line here that best separates the data, and from then on it's just a separation. So this is the downside of the SVM, is that we don't get a kind of We don't kind of get told how close we are to that margin. We just get it's this side or it's this side. Unlike where logistic regression would give you, a probability. Now there are methods whereby you use a number of these by cross validation and try and find out what its probability would be by using it on different validation sets and so on. You can do that in order to try and figure out, well, how well does it do? But in its standard form, it just says it's one side or the other side of the barrier. Okay, so with regard to problems that you come across, the question would then become, well, should you use logistic regression or should you use an SVM? And in truth, you should really be trying both. And that's why in the assignment that I've given you, I've asked you to try out several different classification algorithms, or to compare at least two, because it's a good idea not to assume ahead of time what the best classification model might be, and to try several different models. And generally you'll find that one model works particularly well. When it comes to using SVM, well, you're obviously, it's going to be a good idea to try some of the different kernel methods, particularly if the data is not easy to separate, and if it's high dimensional data, which you're going to have. You're not just dealing with two-dimensional data, you're dealing with, I think there's 14 dimensions in that assignment I've given you. You're still, I'm suggesting to you, only have a binary classification, but so you're going to have a positive class or negative class. You can have multi-class SVM as well, where it basically decides which of the classes it should go for, and it'll come up with a prediction of which class it is. But what I'm saying to you is that you should be trying all of these different ones, and they're relatively easy. It's not like you have to write the code for these. If you go to Scikit-Learn, you're going to find that people have tried all these different things before. So while your data is different, the design of the models is not. So you'll find that there's library functions there for doing logistic regression, there's library functions there for doing SVM, and there's library functions there for doing the different kernel functions as part of that. So you can try the polynomial, and you can try the degree of it, or you can try the radial basis function on your data. And generally these will run pretty quick. Do just be aware that particularly with something like the polynomial, if you go to a high degree of polynomial, that problem becomes a good deal more complex, and you might find that your computer is running for quite some time before it's able to separate out the data. So do just be aware of that. Okay. So just obviously finish off with a few acknowledgements for this. Andrew Ng and Scikit-Learn were both very helpful in this. And there was a GitHub page that I used for setting me up with the nice models that we used here. So again, you can search people's GitHub pages and find there's particular people have some very good examples of code. If you're using something from GitHub, of course, you need to reference it. You need to give people credit where credit is due, and also not pass off work as your own that belongs to somebody else. So we'll leave it there for tonight, guys.